Section: Introduction. In this section, we discuss the impressive abilities of large language models, LLMs, in handling complex tasks, making them suitable for autonomous decision-making in dynamic settings like multi-turn tool use and navigating graphical user interfaces. We recognize that reinforcement learning, RL, plays a crucial role in enhancing the capabilities of LLMs by optimizing their performance through feedback from interactions. A key requirement for effectively training LLM agents with RL is having a diverse set of high-quality tasks for them to learn from. However, creating these tasks manually is expensive and not scalable, highlighting the need for an automated system to generate tasks. While previous research has developed specific pipelines for task synthesis in areas like collaborative design and web navigation, a general approach for multi-turn LLM agents in versatile environments is still lacking. To create a synthetic task generation pipeline, we can draw inspiration from how human annotators design tasks by first exploring tools and environments to identify achievable goals. We propose a self-challenging agent framework, where the agent takes on two roles. As a challenger, it interacts with an unfamiliar environment to generate potential tasks, and as an executor, it attempts to complete these tasks. We face challenges in ensuring that the generated tasks are feasible, verifiable, and appropriately difficult. If the challenger produces flawed tasks, it could negatively impact the training of the executor. To address this, we introduce the Code as Task (CAT) formalism, which structures each task with four components: an instruction, a verification function, an example solution, and a list of potential failure cases. This structure helps ensure that tasks are practical and can be verified through executable criteria. By using external code executors, we can filter out low-quality tasks, enhancing the overall training process. Our experiments involve 4 different tool use environments, where we generate synthetic tasks and use them to fine-tune the LLM agent before testing it on existing tasks. We demonstrate the effectiveness of our self-challenging agent framework in 2 scenarios: distillation, where we improve a weaker model by transferring knowledge from a stronger one, and self-improvement, where the weaker model learns independently. In distillation, we achieve a 20.2% improvement in success rates across all environments without prior tasks. In self-improvement, our framework doubles the success rate from 12.0% to 23.5%, surpassing previous methods. We also explore the concept of self-challenging agents, which has been previously examined but not in the context of open-ended tool use environments. Our work builds on this by introducing the Code as Task formalism, ensuring that generated tasks are feasible and verifiable. Additionally, we highlight the potential of LLMs to autonomously evaluate their performance and improve through self-generated tasks, although previous methods lacked mechanisms for ensuring task quality. Our approach significantly enhances task quality by grounding tasks in the Code as Task format and utilizing external code executors. Finally, we note that while LLMs can be equipped with external tools to enhance their capabilities, the use of code as a universal interface for generating synthetic tasks has not been thoroughly explored. Our work proposes a novel Code as Task format that formalizes tasks to ensure their quality in diverse, tool-rich environments for LLM agents. Section Summary. In this section, we discuss the development of a self-challenging agent framework that synthesizes high-quality tasks for multi-turn LLM agents by having the agent first explore an environment to generate tasks and then attempt to complete them. We introduce the Code as Task formalism to ensure these tasks are feasible, verifiable, and challenging, significantly improving the training process and performance of LLM agents in various tool use environments. Section: Problem Setup. In this section, we outline the problem setup for our LLM agent. In a typical scenario, our agent aims to complete a specific task. Acting as an executor, the agent interacts with an environment that includes various tools like a code interpreter, web browser, and even human users. We denote the agent's behavior as the executor policy. At each step, the policy generates an action, which could be a code snippet or a question directed at a user. The agent then observes the response from the tool or user and adds this information to its context for deciding the next action. Each action also influences the environment, changing its state, which we represent through a transition function. The initial observation may contain useful details, such as API documentation or task instructions, which can be clarified through user interaction. Once the agent completes the task after a set number of steps, we use a verification method to assess the solution's success and provide a reward. We recognize that interactions between a language model agent and its environment can be viewed as a form of tool use. This framework for multi-turn tool use language agents covers various tasks, including coding, web browsing, and user interactions. However, we assume an unsupervised training setup where we lack access to the true task set and verification functions. Instead, we introduce self-challenging, which allows the LLM agent to create its own tasks and evaluation functions for reinforcement learning training. We will elaborate on our method in the following section. Next, we present our self-challenging framework for training LLM agents. Unlike the standard setting, our approach gives agents two roles. 1. As a task challenger, the agent interacts with the environment to create high-quality and challenging tasks in a new format called code as task. 2. As a task executor, the agent learns to solve these self-created tasks, which helps it tackle real tasks during testing, especially when annotated data is scarce. We will explain each role in detail. In the task challenger role, the agent engages with the environment to construct a viable task. By accessing various tools, the challenger gathers information about what tasks can be performed. We denote the policy of the task challenger similarly to the executor policy. The challenger takes actions to call different tools and ultimately must produce a task specification that includes a verification function. This process allows us to compile a set of synthetic tasks for training the executor agent. Although the generated tasks may not perfectly match real-world tasks, training on these synthetic tasks can enhance performance on actual tasks, provided there are shared similarities. We also introduce the code as task, CAT, class of tasks. For the task challenger policy to generate high-quality tasks, it must reliably gather information about the environment and unobserved states. This can be challenging, and sometimes the tasks generated may be infeasible or unclear. To mitigate this, we propose the CAT class, which helps filter out low-quality tasks. CATs use code as a means to automatically evaluate the quality of synthetic tasks. Each CAT includes an instruction and a verification function that provides a binary reward based on whether the final state and answer meet the criteria. However, we acknowledge the potential for false negatives and positives during task generation. To address these issues, we add components like an example solution and 3 failure cases, which are checked against the verification function to ensure tasks are both feasible and meaningful. Our experiments show that this approach significantly improves task quality. We provide a specific prompt to guide the task challenger in adhering to the CAT format and producing all necessary components. An example of a complete CAT output is available in the appendix. Section Summary. In this section, we outline our self-challenging framework for training LLM agents, where the agent assumes 2 roles. A task challenger that generates synthetic tasks and a task executor that learns to solve these tasks. We introduce the code as task, CAT, class to ensure high-quality task generation by incorporating verification functions and examples, which helps filter out low-quality tasks and improve training outcomes. Section: Task Executor. In this section, we discuss how we can utilize high-quality tasks generated through the CAT formalism to train our task executor. We explore 2 main approaches for this training. First, we look at self-improvement, where both our task executor and task generator are the same large language model, LLM. After generating a set of high-quality tasks, we use this LLM to gather data and assign rewards based on verification functions included in the tasks. We then apply reinforcement learning, RL, to optimize the policy. Specifically, we use a basic RL method called one-step reinforce, which focuses on successful outcomes. This approach is similar to supervised fine-tuning, where we refine our model based on successful task completions. Next, we consider distillation, where we transfer knowledge from a stronger LLM to a weaker one using synthetic tasks. This is particularly useful when deploying a larger model is impractical due to cost or speed. After generating high-quality tasks, we use the stronger LLM to create a dataset of trajectories. We then train the weaker LLM using supervised fine-tuning with cross-entropy loss. Our initial experiments suggest that even unsuccessful attempts from the stronger model can provide valuable learning opportunities for the weaker model. We evaluate our self-challenging agent (SCA) framework in various tool-rich and open-ended environments, training agents in both self-improvement and distillation settings using only synthesized data. We measure performance on real test tasks and compare it against baseline models, including conducting ablation studies and analyzing data scaling results. Our experiments take place in 2 multi-turn tool use benchmarks, featuring tasks from 4 different environments with functional verifiers for reliable evaluation. In these environments, we instruct the agent to articulate its thoughts before executing Python function calls or responding to a simulated user. The results from these executions serve as observations for the next steps, with a maximum of 15 steps allowed in each environment. We utilize the M-Cube tool eval benchmark, where task success is determined by matching the agent's final answer to a reference solution. We report performance in both calculation and web browsing environments, where the calculation environment involves using various tools for computations. The TauBench environment focuses on customer service interactions, requiring the agent to engage with a simulated user and make database modifications. We employ around 15 tools in each environment to facilitate these tasks. Section Summary. In this section, we explore training a task executor using high-quality tasks generated through the CAT formalism, focusing on 2 methods: self-improvement, where the same LLM enhances its performance through reinforcement learning on its own trajectories, and distillation, where a stronger LLM transfers knowledge to a weaker one using synthetic tasks. We evaluate our self-challenging agent framework in various environments, measuring performance against baselines and analyzing results from both self-improvement and distillation settings. Section: Main Comparisons. In this section, we describe our experimental setup and comparisons. We fine-tune the LLaMA 3.1 to 8b instruct model, referred to as Llama-3.1-8b, as our base model for reinforcement learning. In both the distillation and self-improvement scenarios, we use the same fixed LLaMA 3.1 to 8b model as the task challenger. For self-improvement, all training tasks and trajectories are generated by Llama-3.1-8b itself. In the distillation scenario, we utilize the larger LLaMA 3.1 to 70b instruct model to sample demonstration trajectories. We compare our method, SCA, with several baselines across different settings. First, we assess the zero-shot performance of both LLaMA 3.1 to 8b and LLaMA 3.1 to 70b to see how much improvement SCA can achieve from the pre-trained model. We also use GPT-4o as a reference for advanced proprietary models. Additionally, we compare with the Proposer Agent Evaluator (PEA) baseline, which has been effective for task synthesis and autonomous improvement in open-ended GUI navigation. In PEA, tasks are proposed by prompting LLaMA 3.1 to 8b with initial observations, like API documentation or a web page. Success is evaluated by prompting the same model with the instruction and the resulting trajectory. The key differences between PEA and SCA are: 1. PEA generates tasks directly from initial observations without actively gathering information. 2. PEA only creates instructions, while our CAT tasks include instructions, verification functions, example solutions, and failure cases. And 3. PEA uses the same model for evaluation instead of relying on verification functions like SCA does. The third point mainly affects the self-improvement setting since all demonstration trajectories are used in the distillation setting. In the distillation results, we note significant generalization to out-of-distribution test tasks from training on synthetic tasks. Both PEI and SCA achieve over 18% and 20% absolute improvement in average success rates, respectively, despite the differences between synthetic and real tasks. However, PEI has limitations, such as proposing ambiguous tasks based on limited initial information. While PEI performs well in straightforward environments like calculation, with a 23% improvement in success rate, its tasks do not encourage the teacher model to provide diverse demonstrations in partially observable environments. In these cases, the task challenger agent in SCA excels by actively exploring the environment, leading to more precise tasks and better performance, with gains of up to 5.2% in success rate in retail. In the self-improvement results, we find that the quality of synthetic tasks is crucial. While PEI is effective in the fully observable calculation environment, achieving a 7.3% improvement, it struggles in the other partially observable environments, even resulting in a 10% drop in performance in airline. In contrast, SCA benefits from the diversity and precision of tasks generated by the task challenger agent, achieving an average gain of 11.5% compared to the base model and a 10.6% advantage over PEI in Pass at 1. This highlights SCA's superiority in tool-rich and open-ended environments compared to the PEI, which relies heavily on fully observable conditions. Section Summary. In this section, we detail our experimental setup for fine-tuning the LLAMA 3.1 to 8B model and compare our SCA approach against the PEI baseline across various settings. Our results indicate that SCA outperforms PEI, particularly in partially observable environments, by generating more precise tasks and achieving significant improvements in success rates, highlighting the importance of task quality in self-improvement scenarios. Section: Analysis and Ablations. In this section, we explore how different reinforcement learning (RL) algorithms interact with self-improvement through contextualization (SCA). The main self-improvement results, as shown in our main table, come from simple rejection fine-tuning on successful offline rollout trajectories. However, SCA is designed to work with any RL algorithm, including advanced online methods like proximal policy optimization (PPO) and generalized rejection policy optimization (GRPO). We examine the effectiveness of SCA with various RL algorithms and present our findings in a figure that includes both offline methods like rejection fine-tuning and DPO, as well as online methods like GRPO and PPO. While offline methods can achieve notable self-improvements, increasing from a 20.3% to a 31.8% success rate, online RL can enhance performance even further to 43.2%. However, this improvement comes with added complexity in infrastructure and potential instability in hyperparameters. For instance, we observed that GRPO's performance can drop to 0 at the end of training if not carefully tuned. Next, we investigate the impact of different components in our contextualized task (CAT) framework. We conduct human annotation experiments comparing 4 task generation variants, including a baseline and 3 versions of CAT with varying components. We find that for the variant with only the instruction and verification function, 47.7% of tasks remain after filtering for runnable code. In contrast, the variant that includes solutions sees only 9.5% of tasks pass the verification function, while the full CAT variant has a passing rate of 5.2%. For each variant, we collect 50 passing synthetic tasks and analyze 50 rollout trajectories from LLAMA 3.1 to 8B in a retail environment. We categorize the results into 4 types: false negatives, tasks that are impossible; false positives, tasks that seem completed but aren't; true negatives, mistakes made by the agent; and true positives, correctly completed tasks. Our analysis reveals that tasks from the baseline lead to many false negatives due to ambiguous instructions. We find that requiring an example solution helps reduce false negatives but increases false positives, as some verification functions are too lenient. To address this, we can add a filtering mechanism based on failure cases to eliminate false positives in CAT. However, we still encounter a significant number of false negatives, primarily due to incomplete instructions. This issue, which involves nuanced semantic dependencies, remains an open question for future research. We also consider how the automatic filtering in CAT affects task diversity and difficulty. We analyze task difficulty before and after filtering, measuring it by the length of example solutions. Our findings indicate that while the distribution of task difficulty becomes more uniform after filtering, it remains diverse with stronger models. This suggests that CAT filtering primarily removes poor quality tasks without collapsing the overall diversity. Finally, we discuss whether to scale the number of tasks or the number of trajectories per task to enhance performance. Our findings show that increasing the number of interactions consistently improves success rates in the training set. However, these improvements do not always translate to better performance in out-of-distribution test sets. We find that a diverse training set, particularly with 800 tasks, is crucial for steady improvements in test performance. This highlights the need for a large set of training tasks and the potential of SCA to automate large-scale task creation. Section Summary. In this section, we analyze the effectiveness of different reinforcement learning (RL) algorithms with self-improvement via rejection fine-tuning and other methods, finding that while offline methods achieve notable success rates, online methods can significantly enhance performance despite increased complexity and instability. We also investigate the impact of various components in our task generation approach, revealing that while filtering improves task quality, it can lead to a reduction in task diversity, emphasizing the need for a large and diverse set of training tasks for optimal performance. Section: Limitations. In this section, we acknowledge the limitations of our work, which also present future research opportunities. While our LLM agent shows potential in generating high-quality tasks for self-improvement, we still encounter a significant number of false negative examples, as illustrated in the taskbar figure. The main issue arises from semantic nuances, like ambiguity or missing information, which can be hard to identify. This leads to a gap in performance between reinforcement learning training with specific tasks and ideal tasks, as discussed in the additional discussion section. Furthermore, due to the differences in the environments we studied, our LLM agent primarily enhances its skills specific to those environments rather than its overall capabilities. Therefore, improving the general capabilities of LLM agents across various environments remains an open research question.